Hi, I'm Michael Lamoureux, and today I'd like to discuss some non-intuitive cases of induction, wherein the induced EMF is evenly distributed around the circuit rather than concentrated on one part of the circuit. The important thing to know about these cases is that you need to modify Ohm's law to potential difference plus EMF equals current times resistance. The first case, let's imagine a uniform circular loop of wire with 1 ohm resistance. And let's assume there's a time-varying magnetic field linking this loop and inducing 1 volt of EMF in it. So you have 1 volt of EMF with 1 ohm resistance gives you 1 amp of current. Now the interesting thing about this is that there is no potential difference in this loop at all. It's run entirely by EMF, which is non-intuitive. Now for the next case, this diagram here. Let's do it this way. Okay, I have a similar situation, except in this case, let's assume that the wire has negligible resistance. And you have a 1 ohm resistor in the circuit here. Okay, and let's assume that there's 1 volt of EMF induced in the circuit, which will give you, again, 1 ampere of current. Now, the EMF will cause a potential difference of 1 volt across the resistance. Notice there are 2 paths between the ends of the resistor, one through the resistor and the other the wire of the circuit. So the EMF and the potential difference are in opposite directions. Now, because the EMF is evenly distributed around the circuit, half of the circuit will have a half a volt of EMF, a quarter of the circuit, a quarter way around will have a quarter of a volt, and so on. Now let's assume that the resistor is physically small enough so that it's insignificant. And therefore, there is a negligible amount of EMF induced in the resistor. So the potential difference is the only thing determining the current in the resistor. And there's 1 volt of EMF around the circuit and virtually none in the resistor. And you've got 1 volt of potential difference in the opposite direction to the EMF. So they cancel each other out. So there's virtually no voltage around the circuit, which is just what's needed to maintain a current in a negligible resistance of the wire. Okay, for the next example, let's have 2 resistors. 2 5-ohm resistors. I'm no artist, so please assume that all these are perfect circles. Let's assume there's 10 volts of EMF induced in this circuit. And there's 10 ohms total resistance, so that gives, again, 1 ampere current. Now, we'll start at the ground here. It's just a 0 point. Following up, the EMF gradually increases, so you get 2.5 volts of EMF by the time you reach the resistor. Okay, the resistor is bucking the EMF, so you have 2.5 volts of EMF minus the 5 volts across resistor, so that's minus 2.5 volts. Then you gain another 2.5 volts EMF to reach 0 volts at point A. Then continuing on, around you get 2.5 volts down to this resistor, which again bucks it, so you have minus 2.5 volts. And then you gain another 2.5 volts by the time you reach ground, so you get 0 again. For the last example, I have 2 resistors again, but this time they're not symmetrical. You have a 9 ohm resistor and a 1 ohm resistor. Again, let's assume 10 volts of EMF in the total circuit. Again, 10 ohms of total resistance, so you have 1 ampere again. Okay, starting at 0 at the ground, go up, gain 2.5 volts of potential difference, minus 1 volt, 2.5 volts of EMF, minus 1 volt potential difference, that's 1.5 volts. And you add 2.5 volts of EMF, you get 4 volts at point A. Continuing on, you add 2.5 volts to the 4 volts, you get 6.5 volts minus the 9 volts is minus 2.5 volts. You continue on, gain 2.5 volts, and it comes out to 0 again at point B, which is the ground. Thanks for watching. Bye for now.